Okay, students, we are going to finish up chapter 8. We're going to write and graph exponential decay functions. So I'm just going to use the rule that's in the book here. We're going to hone in here. So now, instead of increasing, it's decreasing. And remember, when you have a linear function, you're plussing or subtracting. When you have an exponential function, if it's increasing, you're multiplying, and you can see that the numbers increase much faster. So you can look at a table and figure out a lot of times that it's not a linear function. So decay is the same thing. So tell whether the table represents an exponential function. If so, write a rule for the function. So remember, everything comes from y equals a b to the x power. A is the y-intercept, and then b is whatever the rule is, times x. Okay, so we look here and we have a table of x and y's, and you can see -1, 0, 1, and 2. So we can tell in the x direction everything is increasing by +1. Then you can look here and you can tell we've got 1/9, 1/3, 1, and 3. But we're definitely not adding. So you should be able to tell real quick that it has to be an exponential function. So sometimes, again, don't maybe start with the fractions. Look and see, how do I get 1 to 3? And you can see that's times 3. So start with the ones that are easy to read. Make life easy. Take the math skills that you have and look for ways to make it easy. Then check and see 1/3 times 3. Does that give me 1? And it does. Then take, like I said, you can take your calculator. 1/9 times 3. So if you did it by hand, 1/9 times 3. And that gives you 1/3, right? Because 3 goes into 9. 3 times, and 1 times 1 is 1. 3 times 1 is 1. And so you're getting the correct number. So you can see real quick that you're timesing it by 3. So that is the rule. When I mean the rule, that's the rule, times 3. So that is what b is. A is the y-intercept, which is here when x is 0, is 1/3. So we had just learned that on growth. So here, y equals 1/3 times 3 to the x. Okay? So now, let's look at another one. So here we have, you can hear, I'm recording at school today, so it's a little bit different. You might hear bells. So again, they've given us another chart here, or table, and the x's are increasing by 1. Again, I can tell real quick that you cannot add and get these. And so from 4, what would take me from 4 to 1? So this is what you have to look at. The numbers are decreasing. So that tells you you're going to have to multiply by a fraction, less than 1, most probably. So 4 to 1 is times 1/4. 1 times what will give me 1/4? So that one would be easy to see. And then 1/4 times 1/4. So again, I'll show you, since you guys love fractions. 1/4 times 1/4 would be 1 times 1 is 1. 4 times 4 is 16. So you can see now that you have found b. That's the rule. And the y-intercept is 1. So here, a is 1. B is 1/4. So you can go ahead and you can write a rule. So now, since b is less than 1, this is called a decay function. Okay, and we don't need to write 1 for a. So we don't need to say 1 times 1/4 to the x power. That you notice that in algebra. They don't bother with the 1. You should understand that a is 1. So if you see that, there is an a. So if I saw y equals 1/6 to the power of x, I know that's decay because it's less than 1, and I know that a is 1. All right? So let's move on now to graphing, and we are going to graph a decay function. So we've had a growth function, now we're going to do decay. So let me hone in here. So let's start with 1. So we know that when it was a growth function, it increased. Okay? We saw it increase from left to right. And we're also going to identify the domain and range of this. So what do you think? It's not going to be increasing, all right? So let's go ahead and use the same points that we did before. I'm going to use 0, 1, and 2, and then I'm going to use -1 and -2. So I'm going to use the same values. They fit nicely on the graphing paper that we're going to do. It's always right to start with anything to the 0 power. So remember from our exponent rules here, anything to the 0 power is 1. So 1/2 to the first power is just going to be 1/2. So it's the opposite. See, these positive numbers are actually producing fractions less than 1. If I say 1/2, and I'm going to show down here 1/2 to the second power, that means 1 times 1 is 1. And then it's 2 squared. 2 times 2 is 4. So you can see that as your x values are increasing, your y values are getting smaller. So you're going to see how this is going to change the graph. Then if I plug in a -1, so I want to show my work, I've got 1/2 raised to the -1. So remember, if we have a negative, we're going to go ahead and flip it and make it positive. So by flipping the inside, it becomes 2 over 1, and then the negative exponent here becomes a positive exponent. So then it just becomes 2 to the first power, which is 2. So you can see that x values that are negative are producing positive larger y values. It's the opposite of the growth function. So -2 should give me a bigger y value. So we're going to see in a minute. So I've got 1/2 raised to the -2. So I want to change this to a +2. So that means I have to flip the inside. So it becomes 2 over 1, and now I have a +2. And that just becomes 2 to the second power, which is the same as saying 2 times 2, which is just 4. So look how this graphs now. I'm considering these all 1s. I'm not marking them out. Sometimes you'll see 1, 2, 3, 4, 5. They're marked 1 point, so you can see they're going by 1s. -1, -2, 3, 4, 5. So this would be -5, just so you can tell that it's going by 1s. So 0, 1 is right here. And then at -1, we're going to go up to 2. And then at -2, we're going to go up to 4. So -2, 1, 2, 3, 4. So you can see it's coming from higher up this time, and it's going to go down. So now at 1, we go to 1/2. So at 1, it's about 1/2. And at 2, we go to 1/4. So you can see as the numbers get smaller and smaller that it is going to form that asymptote that I was talking about. So it's going to skim along here, and it's never going to touch it. So it goes the opposite of a growth function. A growth function increases this way. A decay function ends up going down and getting smaller and smaller. Okay? So now we're going to look, and we're going to decide what the domain is. So if I'm looking here, and I want to write this, domain and range, okay? So the domain is not restricted. Even though this is going up, it's covering all the x values and then all the x values this way. So domain is all positive numbers, well, all real numbers, sorry, hopefully you can read that. I'm trying to squeeze it all on the graph. Now the range is the same thing. The range is the y value. So you can see that it does not go below 0. It goes real close to 0. Remember I explained that, and then it goes up this way. So the range is all positive numbers. So you just practice, and then after a while it gets easier and easier to read these graphs. So I'm going to show you one more graph where they compare two different graphs. So let's go ahead and do this real quick. I'm going to open this up here. We're going to look and we're going to make a comparison between y equals 3 times 1/2 to the x, and the other one, I'm just going to do it here so you can see it on the graphing paper, but I will graph them together. Y equals negative 1/3 1/2 to the x. Okay, so we've got a 3, which is positive, and you've got a decay function because 1/2 is less than 1. Then here I have a negative 1/3, and I have a decay function. But let's look at what a positive and a negative is going to produce. So a positive, you should know, is going to come down like this. So we're going to graph both of them. I'm going to do the same points on both of them so we can see clearly. 0, -1, -2, 1 and 2. Okay, then I'm going to put my other here, but I will graph them together on the same coordinate plane. I'll maybe pick a different color, do one green, one pink. All right, same x values. All right, so let's start with this one. Okay, anything to the 0 power is 1. So 1/2 to the 0 power is 1, but then I have to multiply it by 3. So 1 times 3 is 3. So be careful that you're doing that. Then 3 to the 1/2 raised to the first power. 1/2 raised to the first power is 1/2. 1/2 times 3 is just going to be 3/2. All right, then I've got 3, and I've got 1/2 raised to the second power. So remember, order of operations, you always have to do PEMDAS first, so anything with exponents has to be done first. So 1/2 squared, so that's 1/2 times 1/2, that's going to be 1/4. 1 times 1 is 1, 2 squared is 4, so 3 times 1/4, that's just going to be 3/4. So now we're going to do the negative, so I'm trying to do it so we can see all the work and then the graph afterwards. All right, so now I've got 3 1/2 to the -1. So watch, this is going to make the number larger, because remember, to get rid of this -1, I have to flip the fraction inside. It makes it a positive. So 3 becomes 2/1 raised to the first power. 2 raised to the first power is just 2, and 2 times 3 is 6. So just like we said, you should get a positive. All right, then we're going to do the other one. I'm putting it here. 3 1/2, so we should get a larger number raised to the -2. So again, I'm going to flip it. 3, it becomes 2/1 raised to the second power. So 2 squared is 4, 4 times 3 is 12. And I know I do a 10 by 10, so I just kind of wing it a little bit when I'm graphing. So let me graph this. Let me do it in pink. Okay, so this is going to be our positive decay function. So we start at -2 and 12, so somewhere right here. Just improvise a little bit. -1, 6, so x of -1 up 1, 2, 3, 4, 5, 6. There we go. At 0, we've got 3. So that's our y-intercept. That would be A on the graph, right? And at 1, we go to 3/2, which is 1.5. So 1, we go to about 1.5. And then at 2, we go to 3/4. So 2 is at 3/4, so a little bit less than 1. So again, you can see that this is going to skim along here. Forgive my not so great drawing, but you get the idea. So I'm going to do a negative and see how that will compare to a positive, right? So we know that it's a decay, it's coming down, and that's a positive. So let's see how the graph of a negative will go. And I'll graph that one in green so you can see the difference. So a 1/2 raised to the 0 power is just 1. 1 times -1/3 is just going to be -1/3, which you should know because this is your y-intercept, so we know it's passing there. Then let's do 1. 1/2 raised to 1 is 1/2. 1/2 times -1/3, So you all have calculators, so just multiply them together. That's going to give you -1/6. So you can see it's getting really small. 1 times 1, 3 times 2. Now I'm going to do a 2. 1/2 raised to the second power gives me 1/4, and -1/3 times 1/4 is going to give me -1/12. You just multiply straight across, okay? You can simplify anything, so you can see they're very small negative numbers. So here, if I put a -1, so we're going to work the same thing here, and I'm trying to do it so you can see, and then afterwards we'll graph it. So we've got -1/3, we've got 1/2 raised to the -1. So you should know I have to flip now to make this exponent positive. So I've got -1/3, and that becomes 2 to the first power. So -1 times 2 is -2, and then this is considered a 1, so -2/3. Okay, and that's getting a little bit higher than -1/3. All right, it's more negative, but the numbers are getting a little bigger. So -2. So let's show that, and then afterwards we'll plot these points on the graph. I just want to show the work, because I know sometimes with the fractions we got 1/2 raised to the -2. So I'm going to flip that, and it's going to become -1/3. Let me show the working of this. It becomes 2/1, and that becomes a +2. So that becomes 4. 2 squared is 4. 4 times -1/3 is -4/3. Okay, so those are this is my table right here. Okay, trying to put it all on one piece of paper can make it a little bit jumbled up, but if you follow through the video you should be able to see how I'm doing this. So let me go 0, -1/3. So if I'm at 0, -1/3 is right about here. That's my y-intercept. So let's see. I'm going to do -1, and I get -2/3. So -1 and -2/3 is a little bit, that's 1/3. Actually it would be like here. And then at -2, I get a little bit over 1, so you can see this part of the graph is going this way. And actually, let me move that over. I'm trying to show you both at the same time. Okay? At 1, we've got -1/6. Okay? So at 1, -1/6 goes up a little bit closer to 0, and at 2, we've got -1/12. So this part of the graph is going to do this. So again, it's going to be close to 0, but not touch 0. So the pink one, the positive one here, the domain is all real numbers. The range is all positive numbers. You can see the y value on the pink doesn't go below 0. Then the domain on the green, the negative right here, the domain is still all real numbers. All the x's are used from one side to the other, but the range is all negative numbers. You can see it does not go above 0. And so that's something you have to practice, being able to read these graphs. So I'm just having you look. Let me pull out. You can look a little bit at them. You can see them, everything. Okay, so we are going to go ahead and we're going to learn to look at a graph and write a rule. Okay, so I'm just going to go ahead and use the one that they have here, and I'm going to show you. So you know, to write a rule for an exponential function, you have to look. You can see that this is a growth function. It's increasing as it goes from left to right. This is a decay function, all right? So we need to write a rule. To write a rule, I need A and B. A is the y-intercept, okay? So I already have that. So I know that's going to be 10 So 0, 10, so the y-intercept is at 10, but I don't know b, okay? But do they give me a way that I can find b? Do they give me another ordered pair? And you should be able to see here, you're given 1 and 12. Let me autofocus this a little better. Sorry, it looks clearer now. So you have an x and you have a y. So y is 12 and x is 1. Okay? So now we should be able to solve and find what b is. So 12 equals 10, and b to the 1 power is just b. Divide by 10. And if I divide by 10, use our calculator here, you're going to get 1.2 if you don't know. So now I have b and I have a. So I can go back and write a function. Y equals a is 10, right? And then b is 1.2 to the x. And look, it's greater than 1, so it is going to be positive. Okay, so we're going to do decay. So let's look at this one, and you can see obviously it's decay, it's going down. It's the same process. You're given a, you know that a, the y-intercept is at 8, and you have another ordered pair that they've highlighted for you, which is an x of 1 and a y of 4. So you're going to do the same thing, you're just going to plug in. So y equals, I've got 8, b to the x. So I should expect, because it's decay, that b is going to be less than 1. So let's just plug in. I've got a y of 4, I've got 8 for a, b, and then to the x power is 1. So they've made it easy. If I divide 8 into 4, I get 1/2. Remember, don't mess it up and say 8 divided by 4, because that's 2. 4 divided by 8 is 1/2. So now I have everything I need. So b is 1/2. So I like to write mine as a decimal. It doesn't matter. You can write it as a fraction. So the rule is y is 8, 1/2 to the x. And there you go. The b tells you decay or growth. Growth is 1 up. Decay is less than 1. Okay, so be careful, because sometimes they put fractions, and a fraction doesn't mean it's decay. They could give you a fraction of 5/3, which is greater than 1. So be careful about that. So there we go. So now we're showing you real quick. If b is greater than 1, you have growth. If b is less than 1, that's what they're saying here, you have exponential decay. All right? So, and decay happens a lot in real life. So again, we have a word problem. When you buy a car, it decays. You take it off the parking lot. It's not worth what it was. You can find out how much decays. So here, again, it's similar. You have a formula which will be given to you, but you have to understand what it is. So y equals a, parentheses, 1 minus r raised to the t power. T is time, just like before on the growth formula. R is the rate, and a is the initial amount. And 1 minus r is the decay factor. So this will always be given to you, okay? So be careful when they ask you for the decay factor and the decay rate. Decay rate is the percent which you're going to change into a decimal, and the decay factor is 1 minus that rate. So let's just look at a word problem that they've given us in the book and use the one, read it and use it. Okay, the number of acres of ponderosa pine forest decreased, okay, in the western United States from 1996 to 2002. So I'm going to underline that because that has to do with the time, right? By 0.5% annually, so that's yearly. So I always underline stuff that I know I'm going to have to look back on. In 1963, there were about 41 million acres of ponderosa pine forests. Write a function that models the number of acres of ponderosa pine forest in the western United States over time. So I'm just going to read this because everything is here and it makes it nice and easy. Let P be the number of acres in millions. So you always want to signify what your values stand for, and that's what they said they called it P, okay? And let T be the time in years since 1963. The initial value is 41, so we know it's million, but they just use 41 because it's easier to write 41 than 41 million. And the decay rate, when you go back, remember they gave you 0.5%. To take it from a percent to a decimal, you divide by 100. If you have a decimal and you want it as anything as a percent, you multiply. So if I divide by 100, I have to go back 2 places. So that's how they came up with this rate. They've changed the percent to a decimal. Okay, so they plug in. So P equals A, the initial amount was 41, and we do know it's million. And then 1 minus, they changed, they gave us the rate as 0.5%. We changed it to a decimal. And you go ahead and you work this out, 1 minus 0.005, and you end up with P equals 41, 0.995 raised to the T. It's really close to 1 right under it, so you can see that's a decay function. So you always have to write your function first, okay? So this would be the function I'm looking at. Okay? Then B, the second part, to the nearest tenth. Okay? How many million acres of ponderosa pine forest were there in 2002? So you have to count between 1963 and 2002, so you need the time of that, and you should know then that that's 39 years, okay? So that's all you're doing. Once you've got the equation here, you're just plugging in 39. And since it's less than 1, it's going to show how much the forest went down in 39 years. So you plug in 41, 0.995 raised to the 39, and you get approximately 33.7. But we know that's million, so it went from 41 million to 33.7 million acres of ponderosa pine forest in 2002. So hopefully this helps. It just takes some practice, and you guys are awesome. Bless you. We will moving on to a new chapter.